Welcome to Fun with Science. My name is Mr. Ross. Today we're going to do a follow-on to the electricity experiments that we did before, and we're going to do a demonstration of how to get the electricity from where you're generating it to where you're going to use it. My engineers this morning are
Melissa and Jennifer.
Melissa and Jennifer. All right, now, before we had generated some electricity by using, what's this called?
Cell.
This is called a cell, right? And it generates about 1.5 volts of electricity. It has a positive terminal on the top, negative terminal on the bottom, right? Now, electricity, the theory of electricity is it's the flow of electrons. Electrons jumping from atom to atom, from particle to particle, going from one place to the other. And as they move, they take electrical energy and move it from wherever it's being generated out to wherever we're going to use it. Like light the lights in here, run the television cameras, run your refrigerator at home, start your car, all that sort of thing. But I have to have some way to get those electrons, a path for those electrons to go follow. So, and that's usually called a conductor. And I have a conductor here, right? And it's full of little
marbles.
Oh, no, those are electrons. Little blue electrons. It's full of them, right? Just like a piece of wire is full. We've got electrons. It's full of atoms, and there's electrons associated with it. Now, I have a red electron. Melissa, take that red electron. What I want you to do, we have a model of electrical current, right? What I want you to do is I want you to put that red electron over here, right? And guess what? Out the other end, I get another electron. Right, you put one in over there, one comes out over here. Now, let's keep the current flowing. Right? Put another electron in there.
There's no more.
You don't have any more electrons?
No.
So I have to give you this one, right? Now, put that one in there. Right? And I get one out over here. Put another one in.
I don't have any.
You don't have any. So what I have to do is this electron comes out here, I have to give it back to you, right? It has to go around in a circle. Put that one in there, right? Another one. Now then, what do you want? You want this one?
Yeah.
Okay. Have we got the red one out yet?
No.
No, we haven't got the red one. So it's not the same electron that you put in over here. It's coming out over here, right? It's another one. What it is these electrons are all negatively charged, right? And we found out when we did static electricity that like charges do what? They repel.
Yeah.
So when you put an electron in there, it's going to repel the one next to it, which repels the one next to it, and gives me one over here again, right? That's an electrical circuit, right? You put in an electron, it comes out, comes back to where the source is, and we do another one. Same thing. All the electrons running out on the table, right? Same thing with this battery. If we want to take this battery, or cell, is a proper name for it, and we want to get the electrons out of the cell, run out and light a little light bulb, right? We can't just take and hook it up to the light bulb and let the light bulb dangle out in the air. We have to have the circuit come back. So what I've got, very scientific instrument, a little piece of wood, I have a cell taped to it, I have some bent paper clips to make contacts with it, and I have a little piece of wire soldered to the paper clip. Right, that's a conductor, so the electricity can flow through the wire. This is called a pigtail. Don't laugh, it's a pigtail. It's like a little pigtail. I have one on the other end, right, with an alligator clip. And the reason I did that is to make it easy to hook up the battery, or hook up the cell, right, because it's a little hard to hold these things all together and then try to hold wires on them. The other thing I have is a light bulb. Same thing. What's this called?
Pigtail.
Pigtail, right? A pigtail. And this little thing on the end?
An alligator clip.
It's an alligator clip, right? So then we have a switch, right? Another little piece of wood, a paper clip, a thumbtack with a pigtail on it, and the paper clip's got soldered to it, another pigtail and another alligator clip. And as long as this is up like this, right, this switch is open, and it's like turning off the light switch on the wall over here and turning the lights out, right? Then when we push down on it,
It's going to turn on.
it should turn on lights. Okay, so now then what we're going to do, let's hook up a circuit. All right, let's take our cell and my little alligator clip. I have a cell and a switch, and then I take my switch and I hook the light to it. Right, now then, if I push the switch closed, should the light?
Yep.
Yes.
You think it should? Did it?
No,
Don't you need another
because that one
battery?
has to be connected.
Yeah.
Why?
So it
Because like
can
the
flow,
tube thing. you have
So
to
the
go around
electrons
circle.
can do what?
move around.
They can move around and come back, right? It's just like our circuit we had here. You put one in, one comes out over here, we gotta put it back over here because we only have a certain number of electrons. There's lots of them in here, but there's only a certain number, right? So, you say that I should hook this up here like this. So that if I take a look at it now, I've got pigtail out, now, connected to the switch, back to the light bulb, back over here. Now then, if you push the switch closed, what should happen?
Turns on.
The light came on. So what's happening to the electrons when you close the switch?
Going around circles.
Electrons at what charge do they have, Melissa?
Positive? No,
Negative, okay. So
Negative.
this is the negative side of the cell. So what's happening is when you close the switch, the electrons are flowing out through here, through the light bulb, right? And back around through the switch and back to the positive side of the battery. And as long as the chemistry in the battery is still good, we haven't worn out all the chemicals, right, we can light the light bulb. Right? So, let's take and change light bulbs for a moment. All right, see what happens now.
Turns on a little.
Turns on just a little bit.
Yeah.
Okay, the reason for that is, when we talked the last time, we talked about some resistance, right, which is the resistance of the electrons going through the circuit, right? So, what is, this light bulb has more resistance than this one, right? So there's not as many electrons flowing around through there. Now, what's pushing the electrons?
The cell.
The cell, right? The voltage out of the cell. And this is what? 1.5 volts,
Yeah,
right? And I have another
1.5.
1.5 volts. What would happen if I took and I hooked them up in series like this, right? The positive side to the negative to the positive. Now then, these two together would put out how much?
3.
3 volts. Okay, and I'm going to hook it over here, and it didn't light. Well, how come it didn't light?
You have to connect it to the positive to positive.
Hmm?
Don't you have to connect it to the positive with the positive and the negative?
All right, try it now. Did it get brighter?
Yep.
It got brighter. Huh? What would happen, because I have now, instead of 1.5 volts pushing electrons through that resistance, I have 3
3.
volts, right? If I put another one on,
4.5.
so I'm going to have 4.5 volts, right?
Even brighter.
Do you agree with her? Did it get
Yeah.
brighter? Got brighter, right? Because there's more voltage here pushing electrons, more current around through that higher resistant light bulb. Now this poor little old light bulb, this one's designed to use 1.5 volts. That's why it got so bright. If I were to hook it up to this right now, what do you think would happen if I were to replace it in here?
Be really bright.
Yeah, it'd be really bright for a very short period of time. It'd be so bright, what would happen is it gets so hot and it would burn out the light bulb. Right, so if we were to put it into this circuit right now, right, it'd be really, really, really bright, and we would burn it out. So if we get too much voltage applied to this, you're right, too bright. What happens if I take this one, and we're going to put 2 light bulbs in? What happens now? Are they
both just work a little bit.
They're both lit up just a little bit, right? But they're not as bright as what they were before, right? So what do I have? As I have actually, how many volts did you say I had?
4.5.
4.5 volts, right? So if I have 4.5 volts, then really what is happening is half of the voltage, like 2.25 across here and 2.25 across here, right? And the voltage is divided across those two light bulbs, and we have like half the current flowing through them. Right? Try it again.
It's connected to the battery.
Happening.
Nothing's happening. Why?
It's not connected to the cell.
It's not connected. Why? Why does that make a difference? I got a wire hooked up for the battery.
Because you
from
need
the
the
cell.
energy.
It can't go back around.
They can't go back around. Now, we just had Christmas, right?
Yep.
Those crazy Christmas lights when one's burned out. They all go out because they're
Connected.
connected. So if we take this and we put them up like that. Right? Now, let me do another thing. Right. Let's take these two light bulbs. Right? And I'm going to hook them up like this. If my fingers will work, I'm going to hook them up like this. And I'll hold it. Now, what about it? They both lit, right?
They're brighter.
And they're brighter, okay? Because what I've done is I put them in parallel so that the electrons can flow in parallel around it, right? And if I take now and let's take and undo one. Right? Try it now.
Just one.
Just one lit. Where before, if we had one that didn't light, one like this one was burned out, both of them were out. Now then, this one's burned out, but the other one still lights. Now, some of the Christmas tree lights that you had were where one light could be out, right, and they would all burn, right, because they're hooked up like this. They're actually hooked up in what we call parallel, right? So that even if we have electrons running through here, right, they go down these two parallel paths. Some go through here, some go through here, and back to the source, right? But even if this one's undone, right, or loose, burned out, right, there's still a path for the electrons to get back to the source, so that light bulb over there would light. Right? Question?
No.
No?
No.
Okay. So what I want you to do, I want you to take and hook up 3 light bulbs now. Think that's good? All right. Try it.
These ones.
That one don't have a light. Oh.
This one's lit. It's just not very bright. Okay. If you look at it real close, you can see it glowing just a wee little bit. Okay. So that is an electric circuit, right? Just like the lights up here. There's hooked to a switch somewhere that turned them on, right? And the power, the electrons are coming from Seabrook Power Plant, a nuclear power plant up the road on the shore. It's coming down a wire, coming into the building, right? Goes through that light bulb, lights it up, and guess where it goes then? Back to Seabrook. It has to get back to Seabrook because they only have so many electrons up there too, all right? And when they poke them in the end of the wire up there, they got to get one back, right? So they have another one to poke in the end of the wire. Okay. What's this?
Compass.
The compass. All right? And it's pointing towards you, which you must be
North.
north, right? Why does it point towards the north? Do you have any idea? Right. There's like a big magnet running down through the earth, right? And there are magnetic lines of force are surrounding the earth, right? Going from the North Pole to the South Pole, right? And this is a little magnet in here. And what it tries to do is to line up with
North.
those magnetic lines of force and point north, right? And this side points south. Right, so what I have now, I got another scientific instrument. I have a little piece of plexiglass, and it has a little compass thing on it. It says north, east, south, and west, right? And I have a little needle, right? Little tiny, tiny needle, right? Which is a little magnet, little tiny magnet. So if I take that little tiny magnet and I set it down here, right, guess what? It points north also, right? And it's lining up right now with the magnetic lines of force around the Earth's magnetic field. All right, I'm going to take one of our batteries over here. And we're going to hook it up to, now I know they probably can't see this on the camera, but what I want you to do is to close the switch and you tell us what happens to
It moved.
it moved. All right. Let's get a little more power to it. Put another battery. Okay. Ouch. The alligator bit me. Okay. Close again. So it moves, right? Why does it move?
Why?
You have any idea why it might move?
The force is moving around.
Yeah, there's some force is making it move, right? Now, remember the other day, we took a piece of wire and we moved it through a magnetic field, and we did what? We generated some electricity, didn't we? Right? Well, it just so happens that if we take and we run electricity through a piece of wire, we generate a magnetic field, right? And what's happening is this little compass is trying to line up with that magnetic field that we generate. Okay? So around that piece of wire, if this were the wire, right, and we run current through it, then there's a magnetic field generated around that wire. Right? And of course, we only have one strand of wire, so it's not really very much of a magnetic field. Right? It's pretty weak, and we have just these little batteries. Okay, now, what I'm going to do is I have a bunch of wire wrapped around here, right? Like when we were generating electricity, the more pieces of wire we put through the magnet, right, and moved it, the more voltage we generated, right? Well, this case, what was going to happen is each one of these little pieces of wire generates a magnetic field. They all add up, right? So we're going to get a much stronger magnetic field when we take and hook this all together here. Don't get bit by the alligators. So now then, if we close that, all right, this is going to generate a little magnetic field. Now what I need to do is I need to find something that's magnetic, right? Close it. You got it closed? Okay, we need to...
It sticks.
Hmm?
It sticks.
Yeah, I generate a magnetic field, right? So, now, I have two magnets. Magnets have
North and south.
north and south pole, and what do we know about them? Is that if we take the two north poles and we try to put them together, what happens?
They go.
That repels, right?
Yeah.
Like poles repel. Opposite poles, north and south, attract. Huh. Okay, so now let's get things out of the way. Just a moment. We're going to take, all right, whoops. What's happening?
Push it.
It's pushing it away. So this is the North Pole. This must also be a North Pole, right? Because I'm pushing it away. What if I took and I reversed my current here, going through it. I just turned the magnet around, right, so that the electrons are running the opposite direction through my magnetic field. And now then,
Attract.
they attract it, right? So, depending on which way the electricity is running through, the electrons are running through that called electromagnet, those coils of wire, determines which end is north and which end is south. One way, in this particular case, this end is be what?
South.
The south. Right? We can try it the other way. And what's it going to do now if I close the switch?
Repel.
It's going to repel it. All right, so now, remember what we did? We took this generator gadget that I had, a big permanent magnet, right? And I had a coil wire on a stick, and I had a propeller on the end of it. And if we put it down in here like this, right? And we generated some electricity when we turned this. Right? Now then, what would happen if I take and I run current through this wire? Put some voltage to it and let electrons run through it. I'm going to generate
Stronger.
I'm going to generate a magnetic field, right? Okay? And like we just showed, that if like poles are going to repel opposite poles, in other words, two south poles will repel, two north poles will repel, a north and south do what?
Attract.
Attract. Okay, so, and we could change the north and south pole by changing the way the current was running through that. So now, if I take this and I run current through it, I generate a little electromagnet, right, on here, and put it inside there, what's going to happen? Like poles are going to repel,
Oh, light poles.
repel, and unlike poles are going to
Attract.
attract. So if it's setting on this shaft, what do you think is going to happen if I do that? If I hook some electricity up to it. Right? I have my cell, right, hooked up to one side of a little contacts over here, and what's happening?
Moving.
It's turning, right? If we get it going real good here. What did I build? A little electric motor. The same kind of motor that runs your refrigerator, runs your fan at home, right? In the summertime, we've got a fan blade on it, so we could use it as a fan. If I turned my electrical current around, right? So just hook it up in the opposite direction, what do you think is going to happen to the fan? It's going to run the same way or a different way?
A different way.
It's going to run in the opposite direction, right? And if I get my finger out of the way, give it a little turn. Sometimes it's hard to get it started. Okay, let go. Don't laugh at my scientific instrument. You should not laugh at a scientist. Right? Is that good?
Yeah.
You like that? So what we're doing is we're running some, maybe I lost a blade, that's all right. We're running some electricity through this coil, right? It generates a magnetic field, right, a little electromagnet, and when the poles are like compared to this, we are going to do what? They're going to repel. Like poles repel. Opposite poles
Attract.
attract. So north and the south would,
Attract.
two norths would,
Repel.
two souths would
Repel.
repel. Right. Okay. So. Now, you have a question?
Yeah.
All right, one thing we didn't do with our light bulbs, right? My other scientific instrument that I have is a pencil. Is that what that is? The pencil?
Yeah.
What did I do to it?
Cut it.
I cut the wood off of the pencil, right? And so that I have just the lead down here, right? Now, is the pencil lead really lead?
No.
What is it? You know?
No.
Okay, it's not really lead. Right? What it is it's graphite, which is a kind of carbon. It's a form of carbon, and some clay. Right? Graphite's a pretty good conductor of electricity. Clay is not. Right? So electricity can run through this, but there's a lot of resistance. Right? So there can't be very much. Depending on how long it is, the more resistance that we have. So if we were to take my light bulbs again. Let's just take one this time. And we need a couple batteries. All right. 2 batteries. All right. My pencil. Put it up there. And my light bulb. No, light bulb's not lit, is it?
No.
Why not?
Because there's no flip and because it's not attached.
Because this is not a complete circuit, right? Right? We don't have a path for the electrons to flow around and get back to where they came from. All right, so what I'm going to do is I'm going to touch it down here on this pencil. Is it lit now?
No.
What happened?
It lit up a little bit.
It lit up a little bit, right? And what
Right.
happened now?
Brighter.
Brighter and brighter. All right, if I get down make it too brighter, it's going to burn up a little bulb out, right? But let's slide this back this way. What happened?
It shut off.
Well,
Oh, so there's a little bit.
there's a little bit, right? A little bit more. All right, that's about it. There it is. Just barely glowing. All right, the reason for that is because the electrons are running out of this battery here, or on this cell, through here, through the light bulb, and then when they get over here to this pencil lead, right, that graphite and clay in there, then they hit some resistance. What it does is it doesn't allow as many electrons to get through. So it's not as many electrons running through there. This little light bulb is not going to get as hot, and therefore it's not going to shine as bright. Right, you want to try it?
Okay.
Now don't break my scientific instruments, please. Did it work?
Yeah.
Right, if you get all the way over, what's going to happen?
It's
It's
gonna.
gonna burn out.
It's going to burn out. Right. Questions now. If we put 2 light bulbs in there, what's going to happen? Do they burn as bright with 2?
No.
No. Right? I put my pencil lead in there, and so I got a lot of lead. It doesn't burn as bright. If I reduce the length of the lead by sliding the slider down, right, it's going to get brighter and brighter because I'm doing what to the resistance? I'm making it lower. The more resistance, the less current, the less the light bulbs are going to light up, right? So if each one of these little light bulbs has some amount of resistance in it, right? So I take, and that's what makes it get hot, right? Because those electrons flowing through that resistance makes it get hot, makes it light up. So if I would put more than one light bulb in there, I'm increasing the resistance, so the amount of current that can run through, right, the circuit is less, so the light bulbs don't burn as bright. And the same thing with my pencil lead. All right, let's do a little review of what we learned today, right? This is called a what?
Cell.
It's a cell, and it puts out how many volts?
1.5.
1.5 volts. If we put 2 of them together,
We get a battery.
we have a battery then, and we get 2 times 1.5, which would be
3.
3 volts.
Volts.
And if I were to put 4 of them together,
6 volts.
I would have 6 volts, right? So with the cell, 2 of them together would make a battery, right? So now, the other thing is we have voltage which pushes the electrons, which is supplied by the battery. It's a chemical reaction inside the battery, next 1.5 volts, right? And that's the force that's going to push the electrons, right? And electrons, if they leave this side of the battery here on the negative side, right? Because electrons are negatively charged, they come off of this side. And if they ever go out and go through a circuit, where do they go? Where do they end up at?
Back in the battery.
Back in the battery. They come back to the positive side. So we have to have a complete circuit for our electricity to work. We had some batteries, right, and our little flashlight light bulbs, right, and we hooked them up. We put a light bulb in here. We ended up getting them to light up, and since there's 3 of them in series like that, right, they don't light very bright. They're pretty
Just a little
dim
bit.
because, and the reason for that is because we got 3 volts here, but we have a lot of resistance. Each one of those light bulbs provides some resistance, which limits the amount of current flowing through the circuit, right? So we don't have enough current in here to heat the light bulb up very hot, so there's just going to go a little bit more current. The hotter the filament gets in the light bulb, and the brighter it's going to get. We had our pencil, at which we took half the wood off of it, and that pencil lead is made up of carbon, graphite, and
Clay.
some clay. And it offers a lot of resistance. Electrons can go through it, but there's some resistance to those electrons flowing. So it's just like the light bulbs, right? This offers some resistance, and we took our light bulb and we hooked it up like this. All right, we're only going to use 1 light bulb this time. And get these out of the way. We don't need those anymore. And as we move it down the slider, what should happen?
The light bulb should light up.
It'll light up, and the closer I get to the connection, the less graphite in between, the less resistance, and the brighter the light bulb's going to get. Go the other way, and it gets dimmer and dimmer and dimmer. Oh, we remember we took a wire and we moved it through a magnetic field and we generated some voltage, right? In this case, what we did is we had a wire and we run some current through it, hooked the battery up here, and what happened to the little compass needle? It moved, right? And it moved to line up with a magnetic field which is generated by the electricity running through the wire. So over there, our motor, what we have is we have several loops of wire. We can run electricity through this, and what's going to happen here?
It's going to spin.
Well, what do we generate when we run electricity through this wire? A magnetic field, right, with the north and the south pole. North pole, we had 2 north poles, what are they going to do?
Repel.
They're going to repel. If we have 2 south poles, what are they going to do?
Repel.
They're going to repel. If we have a north and a south,
Attract.
they're going to attract. So as the current flows through here, it generates the north and south pole. Then if I put it down in between that big permanent magnet I have, right, and as the current flows through there, one side is going to repel, the other side is going to attract, and it's going to spin, right? So that's basically it. Do you have any questions?
Nope.
No? So we're all done for the day, right?